I can always clip that off so I don't forget. Okay, let's go to the quizzes. And that was quiz number 8. And see, I have the advantage of having the answer key, but I hope I don't need it. I shouldn't need it. Let me just open it up as if I were taking, whoops, that's the wrong one. 8. Okay. Okay, number 8. A study is conducted to determine whether a new cancer increases the mean survival time by at least 30 days for a certain type of cancer. Explain in this context, the conclusion of the test if you fail to reject the null hypothesis. Okay, so let's think about what this test asks us. This test is asked to test a new drug, and we're going to measure how long survival time is, right? So let's say that we know that the old survival time is 200 days. Okay, now this study wants to know if the mean survival time for people that are using this drug is at least 30 days more than the mean survival time for the rest of the population. So we're basically asking, is 230 days, is it at least 230 days versus 200 days? Does it increase the mean survival time by 30 days? Okay, so let's say that in fact we don't manage to prove that it doesn't increase survival time by at least 30 days. So let's see, we did not find, but what does that tell us about the new cancer drug? That would, the null hypothesis would be that the survival time for people that didn't take the drug is the same as survival time for people that did take the drug. And the alternative hypothesis is that the survival time for people that took the drug is different or larger than the survival time for people that didn't take the drug. So in this context, we failed to reject the null hypothesis. And so we can't accept the alternative hypothesis. So we did not find data support for the claim that the drug increases mean survival time by at least 30 days. That sounds okay. We conclude that the mean survival time has increased by at least 30 days. Well, doesn't this say that we didn't find that? That in fact, that we failed to reject the null hypothesis, that we weren't able to prove that the null hypothesis that the mean survival time is increased by at least 30 days. The drug was shown to increase mean survival time by at least 30 days. Again, if you read the statement up here, didn't it just say that we can't say that we increase survival time by 30 days? We weren't able to reject the null hypothesis that it wasn't less than 30 days. The p-value was too small to conclude that the mean survival time has increased by at least 30 days. Now that's a tough one. That one there is, so far I think number one looks pretty good. I've discarded these two because they say exactly the opposite. Okay, but this last one, well, let's think about that. What does the p-value represent when we do a t-test? Right, this would be basically a t-test where we're comparing one mean against another. What does a large p-value or a small p-value mean? What is a p-value anyway? So I'm going to ask you that. You don't have a microphone, right? So let me see if you have a microphone here. I'd say, yeah, you don't have a microphone, so I can't. Oh, maybe I can. Nope, doesn't look like you have a microphone. Okay, so type in there. What do you think the p-value means in this context? Probability of being true. Actually, I would phrase it a little bit differently. The p-value is the probability that you would be wrong if you reject a null hypothesis. I guess in a sense that's the probability of that statement being true, that your alternative hypothesis that the drug makes people survive longer is correct. So you could phrase it your way. That wouldn't be so bad. But I like my way better, that the p-value is the probability of getting that extreme a result. In other words, getting a result that says that people survive more than 30 days, probability of getting that if it weren't true. If it was one of those 1% of the time or 4% of the time that we would reject the null hypothesis and be wrong, right? So we want that probability to be small. If that probability is small, then the probability of us being wrong if we reject the null hypothesis is small. So the p-value was too small to conclude that the mean survival time has increased by at least 30 days. Well, in fact, if the p-value is small, we would reject the null hypothesis and say that the drug worked and that indeed people lived at least 30 days longer. So this doesn't match the previous statements that we read up here, right? So that looks wrong to me. That looks wrong to me. That looks wrong to me. That's the only one that rings a little bit true to me. So does that make sense to you? Does that help? I'm pausing because I can't see if you're typing, so I have to wait a little bit. It's one of those things until you hit enter, I can't see it. Can you explain why it's one again? Okay, well, first, we did not find data to support the claim that the drug increases the mean survival time. So remember, our null hypothesis is that there's no difference between the two drugs, that the drug does not increase the survival time, and that there's no difference between using drug and not using the drug. So the first one says we did not find data supporting the claim that the drug increases the mean survival time by at least 30 days. In other words, we were not able to find that the drug increases the mean survival time. We instead found that, which is our null hypothesis, was that there's no difference, right? So in this case, in this study, right, where we failed to reject the null hypothesis, we weren't able to say that they were different, right? So that's just basically the same thing that this says. We didn't have enough data to support the claim that the drug increases the survival time. We didn't have enough data to say that the drug made a difference, that the mean survival time for the two groups was different. So fail to reject the null means we can't tell. Right, exactly. Failing to reject the null hypothesis says that we don't have enough data to reject the idea that the two means are the same. The two mean survival times for people who took the drug versus people who didn't take are the same. We can't reject that idea. That's basically what we say when we reject the null hypothesis. Notice I didn't say that. Notice I absolutely will never say, in fact, we accept the null hypothesis. We didn't prove the null hypothesis, right? We only didn't have enough data to reject the null hypothesis. So in a case like this, you haven't actually proved anything, right? We phrase when we do have enough, a p-value less than 0.05, right? I would say we reject the null hypothesis and we accept the alternative hypothesis. We say we've proven that there is a difference, right? But in the case where we don't reject the null hypothesis, it could be for any number of reasons. It could be because we didn't have large enough sample size. It could be that maybe there was, maybe that we just had the bad luck to, happen to, pick a group that was in our sample that happened to be not very randomly selected, or it could be some other confounder or something like that. But that is the deal here. It's all about starting with the assumption that there's no difference between the two groups or the two values or two means, and making ourselves prove with a certain level of certainty, 95% certainty, or another way of saying that with less than 5% chance of being wrong, that we can say, no, that's the null hypothesis is not true. We reject the null hypothesis and we accept the alternative. But we never just accept the null, because that's not what we've proved. Okay, good. So, and the other questions were, let me go back here. The other questions were 10 and 11, which use data. Okay, let's see. North Carolina. Oh, we're gonna work with that in a second. The percentage of premature infants in North Carolina was lower. Oops. What did I do there? Oh no. Did I pop out of that? No, there it is. I got to move something over on my desktop that you can't see. Percentage of premature and it was lower than the percentage of premature babies in the United States. which was reported as 11.9%. Okay, make sure to sort preemie variable in descending order before running the test. Okay. Percentage of Okay, so so what we're asked about North Carolina, we're going to be working with SPSS, and we'll actually do this as we as an example. So we're going to open up that data set in SPSS. We're going to determine the sample size, okay, percentage of premature infants. There is a variable in that data set that's called that isolates whether or not a baby is premature or not premature based on some definition of the gestation time. Okay, they want to know the sample size, how many babies that were in the total study that were valid samples, the p-value, the probability that a baby was born prematurely. In other words, if it's 500, if there are 800 births and there were 100 that there were 10 that, excuse me, 800 births and there were 80 that were premature, that would be 0.1 or 10%. And the conclusion, type R, if we are willing to reject the null hypothesis. Okay, so we're going to take a look at that. Okay, and let's see. Next one is using test the following hypothesis. Alpha equals 0.05. In other words, our tolerance for error is 5%, as it often is. The mean mother's age in North Carolina was significantly different than the mean mother's age in the United States in 2000, which was reported as 24.9 years old, and so on and so forth. There's a reference given there. We want to know the sample size. We want to know the test statistic, T, what T is equal to. And we want to know the probability of being wrong if we reject the null hypothesis. And the bigger the t-value is, we'll get to that in a second. The bigger the t-value is, the smaller the p-value is going to be. Okay, we'll figure that out in a second. And the conclusion, whether or not we can reject the null hypothesis or not. So we're gonna go through. Yeah, there were 800, I think, total. So we're gonna go. I'm not sure all of them were valid, but we're soon gonna find out. Okay, and the confidence interval for the mean is also in there. I may do question 11 first, and then come back to question 10, because a little bit different process in how we would use SPSS. Okay, so let's move on to SPSS. And as it happens, I think I just actually I started from here. Okay, it's going to give me a warning that my license is expired, but I have a grace period of 30 days to renew it. So we shouldn't have a problem. Hi, Masura. Welcome to the group. Okay, if you have a question, you can type it into the chat box. Right now we're going over a couple of questions from homework number or quiz number 8. Okay. I don't like using this. I'll just there's my warning. Okay, so I'm going to say open data. Now I have the data stored on my desktop. SPSS is a little clunky in terms of its navigation. So I click down here. I'll go to my username, and then I'll go to my desktop from there. And here it is down here. Notice that I can see it here. If we can also import other kinds of files here. We can import SAS files. We can import comma delimited files. We can import Excel files. The only problem is that you got to make sure that it's looking for the right kind of file. So right now it's looking for SPSS data files, which are .sav postscripts, right? But if it's an Excel file, it wouldn't see it. So you have to change it to Excel. So notice now we can see any Excel files that are on my desktop, but it can't see that SPSS file. That seems to have disappeared. So if you have an issue finding a file on SPSS, just make sure you're looking for the right file type, or just go down here to all files, and they'll all appear. And of course, among them will be the one we want right now, which is the, where'd it go? North Carolina birth data. So I'm going to open that up. This is just warning me about the way that SPSS is storing data. There's differences between older versions and newer versions. Just answer yes to that. We're not really concerned about that. Okay, so here we are. It happened to open in the variable view, right? Here's the mother's age, right? It's a little cryptic here because the file name, I mean the variable name is mage, but if I look at the label, which we can type in anything, basically any. Oops, let me undo that. If I look at the label, which see if I can't get in there to modify this. If I look at the label, where I can type in basically any kind of description. The variable name has to be only letters and numbers. Can't be special characters. Can't have spaces. There's a limited length, and I don't think it can start with a number. I think it's got to start with a letter. Might be wrong there, but there's a lot of restrictions on the variable names, right? So in order to make this more palatable in terms of the output, what the charts and tables are going to look like, you can put in a label to represent the variable name MH, age of the mother in years, and that's what will appear instead of MH on any charts or tables that you produce, which make it a lot easier to use those tables and charts elsewhere in other applications. Okay, for instance, in a report or your thesis or a Word document and so on. So if this is blank, the label is blank, it will use the variable name instead. And again, depending on what that is, might be pretty cryptic. So that's one of the variables that we're interested in. We're also interested in whether an infant is premature. Now notice that the mother's age is a numerical variable. If I go all the way over here to measure, I see scalar under measure, right? So scalar is SPSS's way of calling this a numerical variable. It could also be ordinal variable, which is like A, B, C, D, good, fair, poor, or it could be a nominal variable, which is a name or a category, right, as we know. So I'm going to leave it there as a scalar variable. Scalar variable means that I can calculate means and standard deviations and medians and so on and so forth. Um, Now, keep in mind that SPSS won't prevent you from running other inappropriate tests just because you put in just because you correctly identify the variable. So that's why a little bit of knowledge goes along very well with SPSS. You got to be a little bit careful. As they say in Spider-Man, how does it go? With great power comes great responsibility. So at any rate, so if you go down here to premature baby, well, that's a different kind of variable. That's a nominal variable. That's either a yes or a no. So we have, here's the variable name, here's the label that's going to appear on the tables. But now the variable name, the variable that we used here was entered as zeros and ones. One of those represents premature, one of them represents not premature, right? So we have to identify for SPSS in order for it to be able to display the data effectively. We have to tell it which of those we're dealing with. And here under values, if I click in there, you see a little box to the right of it. Click on that, and it'll bring up your value labels. Just like before, you had your variable labels, now you have your value labels. And you can tell it that 0 means infant was not premature, and 1 represents infant was premature, right? So I'm going to go in, if I wanted to, I could enter another value, like for instance 9, and call that missing data, right? And add that in, and anything that was entered as a 9 means that we just didn't know. Okay, so I'm going to remove that because I just wanted to show you how you would enter data in there. I'm going to cancel instead of OK. You would normally hit OK after you hit add. So I'm going to go in here and do this. Now notice one of the things here is that 0 represents not premature, and 1 represents that the infant was premature. Okay, so, there's a little bit of a problem with that. SPSS tends to organize data alphabetically, or really in terms of computers, in terms of the ASCII value. ASCII is a special digital number that's stored that represents the number 0 or the number 1 or the letter A, capital A, or the letter B or lowercase b. that there's a different ASCII number. There's 256 of 128 or 256 of them, depending on the kind of system. And they each represent different symbols and numbers and so on and so forth. It tends to organize those in the order of ASCII characters, which is basically alphabetical. Okay, so what's happening here is that when I find a proportion, it's going to tend to want to give me the information in terms of whether an infant was premature over the total number of infants. In other words, if I ask it to give me the proportion, it's going to give me the proportion of not premature infants. So that might be 80% or 90% or 95% or 99%, which is real. But really, I'm usually interested in when this is, we know that it's less common to have a premature infant. So in most cases, you're probably going to be saying to yourself, gee, the better way to do this would be to say, well, what percentage of infants were premature, not what percentage were not immature when you were trying to make a comparison, right? Well, 3% were immature in this population and 11% in this population, rather than, well, 97% were not, and 98. So we tend to work better that way, work more easily that way. So in that problem, it said something about sorting the infants in a certain ascending or descending. I'm going to even go one step further, so maybe we can avoid doing that. I'm going to reverse these two for our purposes. So I'm going to say, okay, I'm going to click on this one. I'm not sure. Okay. I'm going to change this. I'm going to say infant was premature. So I'm going to say that 0 represents the infant was premature. And I'm going to say infant was not premature for the number 1. Click change, and I'm going to say OK. So instead of sorting them, now they'll sort naturally. So I don't have to bother with that later on. So you see, is that okay with you guys? Did you see that subtle change that I made just to make it easier for me? Now, it's still correct, right? The people that are premature, the infants premature, are still going to be identified correctly, right? Because I changed, in addition to, did I screw that up? Hang on a second. Am I wrong about that? 0. 0 used to be, let me think about this for a second. I messed that up. Let's see, 0 was premature. Actually, I can't do that, can I? Because I just changed the definitions, didn't I? Oh, no, wait a second. I didn't change it. Okay, so 0, the zeros represent infants that were not I can't do that, can I? Boy, that would be a mess, right? I actually have to change the numbers so that 0, 1, the lower number represents the premature infant. Yeah, actually, ignore what I just did. I'm going to say cancel. Ignore what I just did. Actually, I should go back and correct this. So make sure that this doesn't get out into the wild this way. Infant was not premature. And this one is infant was premature. Okay, I can't just do that because I didn't change the data. I'm going to do something even more interesting now. Okay, so that's a little bit of an issue for us, right? Because it's kind of inconvenient that it's that way, right? So I'm going to show you something even a little bit more interesting. Okay, so I'm going to go back. It looks like I just screwed something up here. Infant was not premature 0. Not. Okay, that's better. Okay, so infant, I still have the same problem now, right? So I am going to go in here. I'm going to go to the data view so we can see these things. Here's our variable for premature infants, right? Most of them are not premature. A few of them are. But I want to, there's a couple of ways I could deal with this. One way is I could go over here and say sort ascending, sort descending. That's one possibility, right? It's a little sloppy. I still will run into some problems in some calculations in SPSS. I can actually make a new variable. I'm going to go up here to transform, and I'm going to say recode into different variables. Okay, so I'm going to go in here and I'm going to say this premature baby variable. I'm going to put that in here as my input variable. And I'm going to create an output variable called preemie2, right? And I'm just going to call that premature. Okay, and then I'm going to click into old values and new values. Okay, and I'm going to say that if the old value was 0, make the new value 1. Okay, and I'm going to say add. And I'm going to say if the old value was 1, make the new value 0. So now I have really changed the two variables so that what was 0 is now 1, and what was 1 is now 0. Okay, I hope. Yeah, actually, let's do that. Why not? I like that idea. Okay, so what was 0, which is I want that to be that's infants. Well, I'm going to start with 1. 1 is the babies that were premature. So the old value 1, I'm going to say, let's make those are the infants that are premature. Let's keep that as 1. Okay, and I'm going to say add. Now the old value for babies that weren't premature is 0. Let's make that 2. Okay, and I'll click add. So now the premature babies are 1, stay 1, and the non-premature babies become 2. And I'm going to click continue. And I'm going to say, okay, if I only wanted to do it for, say, certain women with a particular marital status, I could add a condition under if here, but I want to do it for all of them, so I'm not going to hit click if and add a condition. So I'm going to click change. It changed now it made the new variable. Remember when I chose this numeric variable, output variable, I chose recode into different variables. So it's not going to erase my original variable, right? It's just going to create a new one called preemie2. So I'm going to click OK. Okay, and it just goes through here and gives me. Notice that this text down here represents the process that we just went through. This is in our syntax, SPSS's language, the process that we just went through. Recode this into this variable into these values into a new variable, and assign these variable labels and so on and so forth. And you could actually type this in to the syntax window, tell it to run it, and it'll actually do it. So for our purposes right now, we're not too concerned about that, right? So I'm going to get this output window out of the way and go back to my data window. And let's take a look at my new variable. Well, let's take a look at it. If it was not, well, look, it's coming up with a number instead of a description. Well, that's because now we have to go back into the variable view and we have to code this new variable that we created. So let's see. First of all, number one, we could copy that and say that indeed it says the same thing. Premature infant. In other words, an infant is born at less than 36 weeks, right? Right, because we haven't changed that criteria. And now in our values, there are no values that hasn't been coded yet. So I'm going to click in here and I'm going to click in this box. And now the value 1 represents premature birth, right? And the value 2 represents infant was not premature. And click add. So now our proportions will wind up a little bit neater. So we learned a little bit about recoding and transforming variables and stuff like that. Kind of a side lesson on that, right? In lieu of just sorting it. So let's go back to our data view. Okay, so let's actually do some of this work. So one of the things that we were asked for in that quiz, in quiz 8, is to determine the average age for the mothers in this study. And I think to make some sort of conclusion about whether or not the average age was different than the general population of mothers in the United States. I don't remember the exact numbers, but we can go move forward with that. And if we need to, we can go back there and take a look at it. So first of all, what variable would that be? That would be the variable mother's age, which is a scalar or numeric variable. So we can go ahead and we can determine what the average value is. So the way I do that, or basically any operation, statistical operation, SPSS, I go up to analyze, I can go down to descriptive statistics, I can go into frequencies, which would be for categorical variables. In other words, frequencies is just a count. How many premature babies are there? How many non-premature babies are there? Right? Or I could go into descriptives for descriptive statistics involving numerical variables. Or if I want more detailed numerical variables, statistics, go into explore. So categorical variable, numerical variable, numerical variable. So if I go into descriptives, I could tell it, take the age of the mother. That's the variable I want to work with. You can put more than one in there if you want. And find for me the mean, the standard deviation, so on and so forth. Okay, the range, variance, range, standard error, the mean. Okay, so I'm going to click continue, and I'm going to click OK. Okay, so let's see. What do we wind up here? We wound up with our sample size is 800. Our minimum, let's see, our minimum is 15. Our maximum is 42. And our average age is 26.92. Now we can take that average and we can compare it to the average for the entire country, which is given in that problem. The problem is that, yeah, how can we tell can we say with 95% certainty, less than 5% chance of being wrong? I think it told us the acceptable alpha error was 5%, so it would have to be under 5% wrong, chance of being wrong. Can I say with that level of certainty that this is different from the entire population? Well, the problem here is that if I took any sample, I would not get exactly the same number as the entire population of the United States. It would have to be enormously lucky to get that by chance, even to 2 decimal places, right? So it's going to be a different number. The question is it different enough to say that we can say with less than 5% chance of being wrong that they are real, the two means of the two populations, North Carolina babies and the rest of the country's babies, is really different from this limited sample, right? Well, the deal here is that I can't know just the mean. I need to know my confidence interval. I need to know where my range is, that I can be 95% confident that the true mean for all babies born in North Carolina are mothers. True mean age of mothers in North Carolina is between these two numbers, and then compare it to the number for the United States and see if the number for the United States is outside of that confidence interval. So I can say with 95% certainty that the two means really are different, right? Well, this didn't give me a confidence interval, just gave me the mean. Well, let's go back to analyze. You may remember I said that you can go into descriptive statistics and you can go into explore and you can get a bit more detail. I'm going to go into explore and I'm going to go back to the age of the mother. I'm going to move that into the dependents list. The factor list is something we'll be using later on. The factor list, I can move in something like marital status, a categorical variable. And what SPSS will do is it will break down the average age of the mother by their marital status. So you get two means, one for married mothers, one for single mothers, right? So we're not going to use that right now. But if there's nothing in there, it'll just find the mean for all mothers. So we're going to go into statistics and notice that it already knows it's going to run a whole range of statistics, but it does want to know what confidence interval do you want for the mean? Do you want 90%? Do you want 95? Do you want 99? Well, since we're working with an alpha error of 5%, that was in the question, I believe. Okay, I'm going to leave this at 95%, which is kind of analogous to 95% certainty is basically analogous to 5% chance of being wrong. So I'm going to leave that. Okay, so I'm going to go click OK. Then I'm going to click OK, and SPSS will actually do this calculation for us very quickly. So notice we got the same mean as we did when we did the other version of this, right? So, but this time we got our confidence interval. And how did it calculate the confidence interval? It took the standard deviation of the sample, right? It divided that by the square root of the sample size and calculated a standard error. And then it multiplied the standard error by either 1.96 for a very large sample or the t-score. In fact, SPSS always uses the t-score, even for a very large sample. By say it came out 1.97. 1.97 times this and added it and subtracted it to the mean, just as we would have done by hand, and gotten a confidence interval. And our 95% confidence interval is 26.49 and 27.34. So I'm 95% sure that the true mean for all babies born in North Carolina that year was between 26.49 and 27.34. So if I compare it to the US population, if the US population number is between these two, I can't say with 95% certainty it couldn't be the same. But if it's outside of these two, either lower or higher, I can say with 95% certainty, or as I said, less than 5% chance of being wrong, that indeed North Carolina birth weights, average North Carolina birth weights for all babies is different than the United States birth weights. So this table should give you, these two tables, the number, the mean, the confidence interval, that should basically give you everything you need for that particular problem. Okay, so I'm going to stop for a moment, wait for you to type in. Does that make sense to you guys? Do you have a question about anything I've done so far? Okay. I'm sorry I made that mistake up front, but you want to know something? Sometimes when you make a mistake, it leads you into correcting it and learning a little bit. Like for instance, it gave us an excuse to learn a little bit about recoding variables. I'm gonna wait for a response. Can you review the test statistic? By that, I don't see how. Oh, the test statistic. The test statistic. Oh, that's the t-score. Okay. Did they mention that in this problem? Okay, so now we're getting into. I know what you're asking for. Let me go back to the question, because there was an element to this that's a little bit different. Whoops. Okay. So in question 11, the mean mother's age in North Carolina is significantly different, which was reported. The United States, the mean age of mothers in the United States is 24.9, right? So they're asking you the test statistic T. Well, now we're getting into t-tests, okay? So what is a t-test? Well, I'm going to go back to my SPSS. And what we're doing there is we're saying to ourselves, okay, so now the mean, actually, let me get a piece of paper here. Let's see. There we go. Okay, turn this upside down. There, whoops. There we go. Okay, so let's take a look at this. I know that the mean for the entire United States, for US, is equal to 24.9. Okay, so now I just calculated the average for North Carolina was 26.92. So one of the ways I could look at this is I could see that the 95% confidence interval for the mean, for the true mean, mu for North Carolina, 95% confidence interval for the true mean in North Carolina. Remember, the X bar is what we have to live with because we're taking a sample. We're really interested in that. Okay, the 95% confidence interval is 26.49 to 27.34, right? So we're 95% sure that the true mean is between these two numbers. Well, the fact that this number is outside of this range would suggest that we're 95% sure, or we have an alpha error of less than 0.05, right? We're 95% sure that North Carolina average birth mother's age for in North Carolina is more than the average age for the entire United States. In other words, we feel we can reject the null hypothesis that the mean for the U.S. is the same as the mean for North Carolina, right? Our alternative hypothesis here would be that the two means are not different, right? So we can reject that and accept our alternative hypothesis. Okay, so now, that's kind of sloppy. Statisticians don't really like using the confidence interval in that method. Instead, they use the t-test. And the t-test compares the difference between your sample mean and your population mean for the other population. This is a single sample t-test, keep in mind. It compares these two, right? And it says, how many standard errors are part of these? How likely is it to get that big a difference between these two? So how would you calculate that t statistic? Well, that t statistic is going to be equal to x bar minus the mean, the difference between these two numbers, the two means. Notice that this is for a single sample t-test. If it were a two sample, in other words, we sampled North Carolina and we sampled Virginia, we're comparing the two of them, then we would be doing the mean minus the mean for North Carolina minus the mean for Virginia, right? X bar for Virginia would be on the top here instead of mu, right? But in this case, we know the mean for the population of the United States. We're going to put that over the standard error, right? Standard error is the standard deviation of all repeated samples of that size. In this case, the sample size is 800. Okay, so how would we calculate this? Well, the way we would calculate this is that we calculate our standard deviation from our 800, right? Whatever, and that came up to be, I'm going to do it from here. The standard deviation came up to be 6.1. The standard deviation, 6.1. The standard error is equal to the standard deviation over the square root of the sample size, right? Which is equal to 6.1 over the square root of 800. Well, do I have to do that calculation? No, in fact, SPSS did it for me. The standard error is 0.216, right? So now I can say that how many standard errors apart, how many sample standard deviation or standard errors apart of these? Well, that's going to be equal to 26.92 minus 24.9 over 0.216. And that's going to give us the number of standard errors apart. And we know that for a very large sample, right, if they're more than 1.9 standard deviations apart, that would only happen in less than 5% of the cases. In other words, we're 95% sure that they're different, right? Now, if it's a small sample size, right, if it's a small sample size like 20, we would have to go to our t table and look up what the critical value of t was for degrees of freedom equals 19 for 95% confidence, right? We'd have to look up that t value, and that t value might be t critical, might be something like, I'm going to take a wild guess, 2.06, let's say. I'm making that number up, but probably pretty close, right? And what we would have to see then is our t difference, our t statistic, the number of standard errors apart would have to be at least bigger than 2.06 instead of 1.96 in order to say that these two means are different with less than 5% chance of being wrong. So I'm going to calculate our t-score from this number, except I'm not going to do it the hard way. I'm going to go back to SPSS. If I can find it again. Let me put this down. There we go. Okay, here we go. Here's SPSS. I don't necessarily have to go back, I don't think, to the table. Let me see. Okay, so I'm going to go down to Analyze. You don't necessarily have to go back to the out. If you want, you can go back to the data table, but you can do this from the output also. Here's my data view. Okay, I'm going to go back here and I'm going to say Analyze, Descriptive Statistics, and I'm going to go, well, we already did Explore. This time I want to compare two means, right? Whoops, look at that. It took that away. I'm going to have, actually, it came up differently. On mine, this is a bug in my version, right? I should see a lot more tests here when I see compare the means, right? So I am instead going to do it from the output window because it's going to be a little bit clearer to you, I think. I'm going to go to the output window. So that's in top. I haven't changed anything. It's just the window that's on top. I'm going to click Analyze. I'm going to go down to Compare Means. Notice there's more. It's a little bit easier for me to deal with here because there are more selections. I don't have to go dig down at this other thing. Okay, so I'm going to say compare means this is a one sample t-test. Why is it a one sample t-test? It's a one sample t-test because I only took one sample and I'm comparing the mean of that sample to a known mean for an entire population of the United States, probably some from a very large data set. So that's a one sample t-test. I'm going to click on that and I'm going to tell it, well, I want to compare the mean mean age of mothers in my sample of 800, I want to compare it to the value for the entire United States, which is 24.9 years, right? So it's going to take that. That's our X bar. This is our mu. It's going to take that and run a t-test for us. And the confidence level that we want on the t-test is going to be alpha is 5%, or in other words, a confidence interval of 95%. So I'm going to click OK. And SPSS is going to very quickly go back and do this again and look at what we got here. So here's our single sample t-test. Sample size is 800. Our mean, our standard deviation of our sample, our standard error, all the things that we wanted from before. And now, in addition to that, it actually does this test for us. T is equal to 9.33. The minute we see something like that, that's an enormous number of standard errors apart. The probability of getting that big a difference between these two numbers is probably about 1 in a trillion or something, like certainly 1 in a million, right? So we go over here, degrees of freedom, 799. You could actually look that up on T-table if you had enough detailed one. The probability of getting that big a difference between these two means and being wrong in rejecting the null hypothesis, saying that they're different, right? Probability of that happening is less than 0.001. Notice all we need this to be for us to reject the null hypothesis is less than 0.05. It's far lower than that. It's not really zero, right? You should really look at this as less than 0.001. It's just SPSS will only go to 3 decimal places on this, right? The mean difference is 2 years. There's the confidence interval once again. That's the confidence interval of the difference between the two. Don't worry about that for now. But so our t-score, our test statistic is 9.33. Our p-value is less than 0.001, right? So far less than 0.05. So we can reject the null hypothesis. Okay, so I think that gives us everything we need at this stage to answer that particular question. Are you guys okay with that? Does that make sense to you? Okay, good. Right now, notice what a great tool that SPSS is. Lots of steps, but helpful. Okay, good. All right. Well, actually, once you do this a few times, it's the same routine every time. Every time, if you first identify correctly that, gee, I'm dealing here with a sample mean and I'm comparing it to a population mean, you say, single sample t-test. And no matter what the data is, what the situation is, you're going to do exactly the same thing. You're going to create your null and alternative hypothesis. You're going to decide on what your acceptable alpha is. You're going to get the data. You're going to take the data in SPSS, and you're going to do this process. So the p-value is, I wouldn't put 0. I would probably put p0 is equal to less than 0.001. Okay, so, because 0.000 really doesn't mean anything. Or you could just say less than 0.01, less than 1%, right? Because it is less than 1%. But I wouldn't put 0 down for the probability because it's never 0, really, right? There's always that normal distribution is asymptotic and never really touches 0. So mathematically, that is, it never touches 0. I mean, in real life, it's basically 0. So yeah, it is 0. Right? Basically, a t-score of 9 in real life is, you might as well just call it 0. But technically, it would be better if you just said less than 0.001, for instance. So now let's take a look at proportions. With proportions, we're dealing with the same kind of thing. Now let's go back and look at that problem, the previous problem. Okay, so make sure to sort premium in descending order before running the test. I think they're asking you to do that because they want the results to come out with the percentage of premature births being the p-value, not the percentage of non-premature births. Okay, so using this test following on the percentage of premature births in North Carolina was lower than the percentage in the U.S. in 2001, which was reported as 11.9%. Okay, so we're comparing a sample proportion to a population proportion. We're using the same data set. Want to know the sample size, want to know the p-value, and we want to know our conclusion about the null hypothesis, that there's no difference. Okay, so let's go back to our data set. So this time, we're going to work with our two variables. Here's premature, and here's premature 2. Okay, so let's go over here to analyze. And I'm gonna make kind of a mistake to start off with. I'm gonna say, well, first I'm gonna go to frequencies. Right, I'm gonna go to frequencies. I'm gonna take a look at this premature infants. I'm gonna do both of them. I'm gonna put that one in there. I'm gonna put our new variable in there. I'm gonna ask it to tell me. We don't want means or anything like that. This is the wrong stuff, right? I wonder if it'll give us. No, we don't want that. Okay. Okay, so I'm going to click OK. I'm just going to ask it for basic statistics. We don't want it means and so on and so forth. They're not relevant to this because it's a categorical variable, so I didn't check any of them off. I'm going to click OK. Just take it with everything blank. And it just told, notice when I did the first variable, it told us that the percentage, valid percent, means that didn't include the missing values. Okay, the percentage of infants that were not premature is 88%. In the second case, notice it reversed the two of them. On the top, it told us the percentage of infants that were premature was 11.6%. Got the same result here as we got here, except we changed the two rows. And I changed the two rows because I like the smaller percentage to be on the top for a few reasons. I'm not sure it'll be relevant right now, but it may be at some point. Okay, so I'm going to go back here to analyze. I'm going to go over here to compare means, see if I can't use this to compare means and see what happens if I do this. So I'm going to compare the rate of premature birth to the test value, which I think was 11 point, remember, it was 11 point, I can't see it, you can't see this, it's buried behind something here. It's 11.9%. Okay, I'm going to go back here, 11.9, right? Okay, or actually it'd be 0.119. And let's see if this, remember I was using this before for numerical, for a numerical variable. See what happens here. Okay, let's see. Well, some sort of problem happened here. This came out really weird, didn't it? Well, because it's not a numerical variable, is it? It's a categorical variable. Okay, so instead, I'm going to go back here. I'm going to take a look at this from another perspective. I'm going to go back down here to, and I think probably the best way to do this would be to compare means. And this time I'm going to go into let's see where it's I'm going, sorry, descriptive statistics. This time I'm going to go into something called crosstabs. Crosstabs, you may have noticed that a good way to deal with data like this, is to say, well, we have a couple of things here. We have premature births or not premature births, right? So a good way to deal with this stuff is to simply put it into tables, right? So as you saw before, it might be premature births versus not premature births. And you could be dealing with an entire population or North Carolina, or it could be dealing with the entire population of the United States. So there were so many premature births here, right? And so many non-premature in a total here. So we can get a proportion out of this, right? So I'm going to try and look at it from that perspective here. So I'm going to go here to premature births. Okay, I'm going to use our variable. Okay. And actually, I can't do that here, can I? What did I just do here? Analyze, correlation, regression, descriptive statistics. I don't want to use crosstabs. A ratio. Nope, that's what I want. Yeah. I never use SPSS don't do this very often for proportions. So I'm a little statistics. What do I want here? Cancel. I would probably want risk. 2-year cells. Yeah, no, it won't do it without doing the columns. So what would the columns? Columns would have to be the spike. I don't remember. I don't remember how to do this. Not quite. Compare means. We've got some paired samples t-test. One way and no. No, this is not going to work. Paired samples. T-test. Descriptive statistics. Descriptives. Frequencies. I don't think there's anything in frequencies that'll let me do this. Display frequency tables. Quartiles, mean, centiles, deviation. Done. I don't think this will do it for me. Yeah, I hate to say this. I don't remember how to do it in SPSS. Oh, I can do it. Okay. I really don't remember how to do it. I'm going to do it by hand, just because I'm going to have to consult my younger brain to try and remember how to do this. So what I'm going to do, I'm going to do it by hand for the moment, right? So I'm going to take advantage of SPSS, having calculated the percentage of premature infants as being 11.6%, right? So I'm going to get a new page here, and our p-value, for our sample, I'm going to call that p cap, so I know it's the proportion for a sample, is equal to 0.116, right? I think I didn't screw that up. That's correct, I think. 0.116. SPSS helped me out with that. It was 93 over 800, so it comes out to be, 93 over 800 comes out to be 11.6, okay, or 0.116. Okay, so now my P for the entire U.S. was, and let's see if I can't find that. Did I leave that open? Yes, I did. My P for the entire United States was equal to 11.9%. P for the United States is equal to 11.9%, or 0.119. So now the question is, our null hypothesis is that the proportion for the U.S. is equal to the proportion for North Carolina. I know this. I don't know this for sure. My alternative hypothesis is that the P for the United States does not equal the proportion of premature births for North Carolina. Okay, so I'm starting with this assumption. I'm not going to reject that unless there's less than 5% chance of being wrong. And in order to calculate that, I need to know what the t-score is, what the difference in these two proportions is. The difference in these two proportions that I found, is the difference big enough, far enough apart to say that they're more than, say, roughly 2 standard errors apart, 2 standard deviations of the mean of repeated samples apart. Okay, so the way I'm going to do that, remember t before was equal to x bar minus mu over the standard error. Well, this time, since I'm dealing with proportions, it's equal to p cap minus p for the US over the standard error. Same deal, except now I'm dealing with proportions. Now, standard error is a little bit trickier, isn't it? The standard error is equal to the square root of p times 1 minus p over the sample size. Okay, so let's see what that's going to be for my situation here. So the square root of p is 0.116, times 1 minus p, which would be 0.884, over my sample size, which is 800. Okay, so I'm going to go resolve that. Yeah, that was less than. Okay, so let's go. 0.116 times 0.88, whoops, try it again, 0.116 times 0.884 is equal to this, and I'm going to divide that by 800. And that's equal to that. Now I got to find the square root of that whole thing. Fortunately, I have a scientific calculator here, so I can find the square root pretty easily. And the square root is equal to 0.0113. I'm going to take all 4 of those digits. Is equal to 0.0113. That's what my standard error is equal to. So let's see my t-score. My t-score is equal to 11.9.119 minus 0.116 minus 0.119 over 0.0113. So my t-score is equal to 0.003. Oh, did I do something wrong there? 0.003 over 0.0113. That doesn't look right to me. I did something wrong here. Standard error. 0.884. 116 times 0.884 over my sample size. I think I should be getting a smaller number than that. 0.003. Let me try that again. 0.116. That's 1 minus 0.116. 1 minus 0.116 is 0.884, if I'm correct. Equals this, divided by 800, equals this, and find the square root of that. No, I got it at 0.00. Yeah, that's right. Okay, so my t-score is equal to, actually my t-score is very small. Was that correct? Was that the number that they started with? 11.9? That's a pretty small difference. Where is it? The US is 11.9. Wonder if I got the right numbers here. And the proportion I got from, let me check the proportion I got from SPSS. Yeah, it's 11.6. Well, that's not much difference there, is there? 0.03. Oh, it's 0.0. I'm sorry. 113, 116, 1%. The difference, yeah, that's a problem. 0.003. Why am I having such difficulty with this today? Yeah, not much difference here. Okay, so yeah, bad news here is that it's such a tiny difference. That surprised me. I'll have to check the answer on that. Why did this happen? Was it just a bad example? 0.113, okay. 0.003 divided by 0.011. Okay, and the t, whoops. Did I do that right? Did I do that wrong? Hang on a second. 0.003 divided by 0.0113. So our t-score comes out to be 0.265. 0.265. That's a very small t-score number, right? We wanted to see a t-score number bigger than our critical value of t for a large sample like that is going to be 1.96. That's our critical value. So to reject the null hypothesis, we would have needed a t-score of 1.96. We wound up only with a t-score of 0.265. So if I go back here to my null hypothesis, can I reject my null hypothesis? I'll leave that up to you to tell me. No. Yeah, the reason I hesitated is because I was kind of a little surprised at the result here, because I would have liked to have seen it a little bit more interesting, maybe a closer call or something like that. I'm going to take a moment. Let me just kill the screen for a second, and I'll be right back. I want to just take a moment and check something. I want to go check the answer sheet, and I'm going to turn off my screen for a second. You can probably still hear me. Okay, let's see. No matter how many times I do this, I always wind up with surprises. Let's see. Okay, now let me go back here. Okay, let me go in here. I think it's over here somewhere. And let's see this. And let's say okay. I haven't forgotten you there, so don't go away. Oops. Okay, let's scroll up here. Okay. Okay, deviation. Oh, that's that one. Yeah, okay, let's go back here. That looks good for that. Okay. And test. Yeah, it looks like we're right. Looks like we're at least close enough to result for it to be reasonable, right? So, interesting. Okay. Okay. Yeah, it's a very small difference. It's too small a difference to be significant. And let me just check one other thing here, if I can. Test deviation. There's a standard error here somewhere. Okay, let's just hang on 1 second here. I'll be right. Okay, just stick with me for 1 more second. Let's see. Yeah, I'm gonna have to play with binomial tests. It's really, um, let me turn the screen back on. I'm going to, I'll go back over the test for uh, uh, the t-test for the p-value. I'll go back over that later, but our result is pretty much correct in terms of like, what our conclusion about the null hypothesis is going to be. It's just that I expect it to be a closer call than that. Let's take a look at number 7. I'm not going anywhere. Hang on a second. Let's see. I don't want you to see that. Okay, so let me go back here. I'll go back over. One of the issues here is that remember, binomial distribution is a bit different than the normal distribution, so the rules change a little bit. Let me go back to number 7. So I think maybe that the test for that might be buried in non-parametric tests, but I'll have to go back and take a closer look at that. I usually don't use SPSS for proportions. In that usually when I'm using SPSS for proportions, it's when I'm comparing two groups or exposures, and later on we're going to be learning something called crosstabs and chi-square and risk ratios and so on and so forth. And that's usually the context that I'm using those kind of tests in. So that caught me a little bit by surprise, but you can do it manually pretty easily. Let me go back here to Firefox and let's go to the quiz. Quiz 8, question number 7. The test statistic for testing mu, the null hypothesis of mu is equal to 100 against the alternative mu is not equal to 100, was t is equal to 3.3 with a p-value of 0.001. Which of the following was an appropriate conclusion? Okay, so p is very small, t is bigger than 1.96, right, or bigger than what we would expect. That it doesn't tell us the sample size, but tells the p-value. So that's the probability of being wrong if we reject the null hypothesis, which is less than 0.05. So we would usually reject the null hypothesis in this situation and accept the alternative. Let's see what the answers are. Since the p-value is very small, we conclude that mu is equal to 100. Well, does that sound right? You would basically be saying that the two are the same. They're both 100. But it sounds to me that that's the null hypothesis. And what did we just say about the null hypothesis? We rejected it. So how would you think that would you check that? No, I agree. In order to interpret the results, we must first know the sample size. Normally if this wasn't here, I would say that's true. You need to know the sample size, right? Actually, maybe not, because the reason why you need to know the sample size is to calculate t and to calculate the p-value. But they've done that for you. So they knew the sample size, and this is what they came up with. So we don't need the sample size, but we don't need it to interpret the results here. Normally, if they told us the mean of one group, we took a sample, the mean of one group was 100, and we're comparing it to 105, we would not need to know the sample size to calculate the standard error and the p value, the t value, and the p value, and so on. In that case, yeah, I'd say no there too, right? Since the p-value is very small, we were unable to conclude that mu is equal to 100. Okay. Well, again, would you say yes or no to that? Yeah, I'm not sure about that one either because it depends on how you interpret it, right? If the p-value is very small, basically we reject the idea that they're the same, right? So we're saying that the mu is different than 100, right? So I would say most likely p-values we're unable to conclude that mu is equal to 100. Well, yeah, we decided it's not equal to 100, right? So I guess in a sense we were unable to conclude that it's equal to 100, but but we're sure we're saying that we're sure it's not 100. We're 95% sure it's not 100. Okay, so that's a little ambiguous, but let's go into the next one. Since the p-value is very small, we were unable to conclude that mu is not equal to 100. Well, that's not true. That's in fact our conclusion, right? That it was not equal to 100. That we were able to conclude that, right? So unable, that's not, we don't want to check that because it's saying we weren't able to. Since the p-value is very small, we conclude that mu does not equal to 100. Well, isn't that exactly what we've just done here? We've rejected the null hypothesis that mu is equal to 100, and we're accepting the alternative that it's not equal to 100, right? So I would say that that's true. Now, this one I think is badly worded, that middle one, but this last one is clearly the better answer, right? Wouldn't you say that? Okay, so yeah, I don't like the wording on this one because we're unable to conclude that mu is equal to 100. In other words, we weren't able to say that it's equal to 100, but that's kind of the null hypothesis. So yeah, it's true that it's not equal to, we're saying it's not equal to 100. So we're unable to say and conclude that. But I think what they meant there was that this isn't really proof of whether it's 100 or not. In other words, we can't, remember we said before, we're never proving the null hypothesis. We're only attempting to prove the alternative hypothesis. So this is probably a way of saying that. A slightly awkward way maybe, but so clearly that last one would be the best answer, right? Don't you agree? Okay, so I think it's a good time to call it a day, and I'll actually try to figure out why I can't get SPSS to do that binomial t-test for me, and I suspect I'll tell you right now, I suspect that the right way to do it is buried in here under either under these non-parametric tests, or it could also be maybe this version. Yeah, I just don't remember. Really, compare means. And again, it's messing me up here with the output window, not with it not showing all the. I don't have an output window open anymore. I closed it. I'm gonna have to go back and take a look at that. In the meantime, I'll edit out any of the clumsy stuff that I did today, so that the other students don't realize, how messed up I made this. But hopefully, I didn't confuse you too much. All right, guys, have a good day. Enjoy the rest of your Saturday. Hopefully, maybe the weather will hold out for us a little bit. Okay, take care, guys. Bye.